Hello, my sweet, darling statistical friends. Statistical friends. It's like imaginary friends, but for statisticians, which are kind of sort of one and the same. All right, today we're going to do another critique, and the critique is this paper.
Optimizing acute stroke outcome prediction models, comparison of generalized regression neural networks,
and logistic regressions. Is it just me, or do all scientific papers sound like incredibly pompous? All right, let's have a stab at this, shall we? What this study decided to do was compare two different ways of analyzing data. So in this study, they had a measure of stroke outcomes, and they wanted to compare two different ways to model that. One is logistic regression, and the other is generalized regression neural networks, which I wasn't terribly familiar with until after I read this paper. I'm not going to talk much about that, but if you want me to talk about neural networks sometime, deal. I'm happy to talk about them. In this study, they had two goals. One is to try to identify the key predictors of stroke outcomes, and the other is to determine whether neural networks outperform logistic regression. So they had 216 stroke patients that they divided into a training set and a test set, and they started the analysis with 25 variables, and through various variable selection strategies, which I'll talk about in a minute, they narrowed it down to their top predictors. And the way they did variable selection with logistic regression was to use backwards stepwise regression. And with neural networks, it was something else. And they also used something else, which I'll talk about in a minute, because it was kind of weird. Anyway, their paper showed that neural networks outperformed logistic regression on every metric they used, like area under the curve, accuracy, sensitivity, and kappa. Whatever kappa is. Kappa is like one of those things that has multiple meanings and multiple types of analyses. I don't remember what this one means, but that's the number. And what did they conclude? They concluded that neural networks were way better, more accurate, and they were better able to capture complex relationships. And then they wanted to generalize that anytime you're looking at stroke outcomes, it's always better to use neural networks. So let's get into some criticisms. So what I usually do, and let me say this paper isn't terrible, awful, horrible. I initially picked this because I thought it was terrible, awful, and horrible, and it turns out I just misunderstood what they were trying to do. But it's certainly suboptimal in several ways. So, as I always do, I try to reproduce exactly what they had. And I struggled a bit at first because the data set they provide, I'll show you an image here. In this Excel spreadsheet, they have the training data, and then they have the test data. Problem is, the sample size in this Excel spreadsheet is 167 for the training set. But in the paper, they say it is 168. So the data set that they provide does not match the data set that they actually used. And so I took a wild guess and decided that the 168th row, or this person, should be reclassified as one of the observations in the training set, not in the test data set. And sure enough, as soon as I did that, all my numbers matched almost exactly, which is always reassuring. It always drives me absolutely crazy when I'm trying to reproduce what they have and I can't find a way to reproduce it. Now, when I started trying to reproduce their logistic regression results, I had a devil of a time. It was an atrocity. I could not reproduce their results whatsoever. And they weren't even slightly off. They were massively off. And it was kind of frustrating because it took me several hours. And I realized what they were doing, which I'll talk about more in a minute, is they have a pre-Barthel score. Is that what it's called? I don't remember because in the spreadsheet, it's one column is labeled Barthel and the other one is labeled Bethel. It's Barthel, but they mislabeled it in the data set. But that wasn't the problem. The problem was they dichotomized their pretest score as a 0 and a 1, or a good or bad. And I was using the continuous version as a predictor. I don't know why they categorized the pre-scores into 1s and 0s. And the outcome of interest is stroke outcomes, which comes as a continuous measure, which is the Barthel index. But they decided to categorize it as a 1 and a 0, which I will definitely have things to say about that. So it kind of makes sense if they're dichotomizing the outcome. why not dichotomize the predictor? And yeah, as soon as I switched that, just about everything was the same, but they're not exactly the same. And I'm still puzzled over this. So here are the estimates, and for the most part, they're close, within a couple decimal places. I was able to reproduce table 1 and table 2 within 2 decimal places exactly, but I'm pretty far off in this, and I cannot figure out why that is. And for the most part, they're similar, except for Bethel Pre. I got 3.601, they got 3.061. That seems oddly coincidental that it's just a flipping of the numbers. But then their odds ratio is different than what I did, and so I started hypothesizing maybe at some point in the analysis, they reproduced the table and then they computed the odds ratio by hand. And when they were transcribing the 3.601, they accidentally put 3.061. And then when they computed the odds ratio from that, everything got messed up. Maybe that's what happened. I don't know. But that also doesn't explain why we get differences on the other variables. So I don't know what's happening. And that frustrates me. I don't know why it's different. They shouldn't be different. I mean, sometimes when I see a difference like this, it could be software issues, specifically like how they handle missing data. Like R might be handling missing data differently than SPSS, which is what they used. Except the data set that I have has no missing data. So I don't know why they're different. I wonder if they use a probit model. Let me check that real quick. Nope, they did not use a probit model. So those results are wildly different. All right, so I don't know why they're different. Who knows? Now, let me get to my critiques. And I have tried to order them from like most problematic to least problematic, except for the end one. I'm going to give kind of a big picture critique. So my biggest criticism, as you may have guessed, is that they took a continuous predictor and then they categorized it as good outcome versus bad outcome. Why? It like unnecessarily complicates it, because if you use the original metric, you could use just linear regression. But by categorizing it, now you're using logistic regression, which is way harder to interpret. Why would you do that? Well, sometimes there's clinical utility in saying that that they have the disease versus not, or this is a good stroke outcome versus a bad. That's fine, but you're not making clinical decisions here. You're trying to build a statistical model, and you're just throwing away information. Please do not categorize outcomes. That is the most common massive mistake that people make. Or you might even say it is the dumbest thing that I've seen smart people do. It's taking continuous predictor and then categorize it. And I'm going to leave some links in the description about why it's a terrible idea, including some stuff that I've said before. So, very bad idea to categorize the outcome. My second criticism is how they did variable selection. I had to read between the lines in this one. They basically had like 2 different filtering processes. The first filtering process used univariate tests to do it. So basically what they did was for every predictor variable, they used either a chi-square test or like a univariate logistic regression test to identify those variables which were statistically significant. And then those which were statistically significant, they then included into the multivariate analysis. This is very problematic for a couple reasons. One reason is you're doing multiple comparisons, you're not correcting for those. Normally I don't care about multiple corrections because I don't care what the p-value is. I use so much additional information like Bayes factors and plots and visuals and estimates. I use all that information to make decisions. I don't rely on the p-value, so I'm not concerned about multiple comparisons. And also I'm not concerned about it because I know this is just an exploratory analysis that I'm planning to replicate in the future. But if you are using p-values and p-values exclusively to guide your decision making, and you're not correcting for multiple comparisons, that is problematic. So that's one problem. Another problem, and I think the much bigger problem, is that it ignores the multivariate nature of the data. So these variables are bound to be correlated with one another. And it could be that one variable is like super predictive alone, but when you include other variables, it's not predictive anymore because there's so much multicollinearity. Or it could be that you have 2 variables that interact, but if you only look at the univariate analysis, you wouldn't know that. And it could be that one of these variables you eliminated because it wasn't statistically significant, that when it's included as an interaction effect, suddenly it is statistically significant. So it's just a terrible idea to use a univariate procedure to filter to then include into a multivariate procedure. So that's like a big problem. So that's a pretty big problem. And then once they winnowed down the list of variables to a much smaller, I think they ended up having 7 variables or something like that that were statistically significant with the univariate tests, then they did backward selection. Stepwise regression is terrible for a couple reasons that I'm just going to talk about briefly. One is that it overfits the training data set. So it's going to pick variables that work really well for the sample, but they're probably not going to work very well for the population, or they're not guaranteed to work well for the population. Also, the variable selection algorithm is super unstable. So small, very, very small changes in the data can lead to very different results and different models that we end up settling on. And I saw that as I was trying to reproduce their results. Like, very minor changes would yield drastically different results in the stepwise algorithm. Another problem, particularly with this one, is like I've seen a lot of backward selection use like AIC or BIC, which is fine, kinda, except that backward selection or forward selection sucks. But they used p-values for variable selection, so you are absolutely inflating your probability of making a type 1 error. So I think resoundingly just about every statistician nowadays says never use stepwise regression, either forward selection or backward selection or anything like that. Stepwise regression is terrible. There are so much better algorithms out there for variable selection that we don't need to be using these anymore. They should be stricken from the record. They should be deleted from textbooks. Any mention of stepwise regression should be like saying the name Voldemort in the Harry Potter series. Yeah, like Death Eaters should show up at your door if you use the term variable selection. This is how passionately I feel about this, people. Please, for your own good, don't use stepwise regression. Okay, next problem that I have is how they handled missing data. So they said, continuous covariates with less than 1% of missing digital data could be imputed with the mean value. Okay. Terrible idea. Never, ever, ever, ever replace a missing value with the mean. That artificially shrinks the variance in the model and makes it look like your model fits better than it actually does. That's a bad idea. Now, fortunately, it's probably not that big of a deal because they're talking about variables with less than 1% missing, and so it's going to be, it's super, super unlikely that the 1% that had missing data would drastically change the model. They'd have to be massive outliers to change the model. And even then, with this sample size, it's probably not going to change the model that much. So it's not that big of a deal, but this is a terrible way of handling missing data. All right, but covariates with more than 1% missing data were excluded. I don't know why they chose 1%, but whatever. Missing categorical covariates were recorded as negative. Why? Why not positive? And by the way, I'm assuming what they mean is that like they had a bunch of variables that were like, they were positive for this disease or negative, et cetera, and they just chose to default to negative. But why negative? Why not positive? Not that positive is necessarily better, but what is problematic is that there's no rationale for this rule. And unfortunately, the data set that they post online has no missing data. So I'm assuming that all the missing data has already been filled in with the imputed value, which would either be the mean or the negative. And so there's no way to rerun the analysis without those missing data strategies employed. If I were to do it, I would use some sort of advanced missing data strategy to see if it actually mattered. Well, I'd actually run the model by doing listwise deletion, which is the easiest way to handle it. Basically, delete any rows that has any missing values, and then compare that with a model where I appropriately handle the missing data using either multiple imputation or expectation maximization algorithm or something like that, and see if it actually makes a difference. Usually it doesn't, especially if it's only 1% of the data that are missing. And by the way, random tangent, I used to be a missing data researcher. When I got my PhD, that's what I did, was I did missing data research. And I don't really do that as much anymore. And why? Because it didn't seem to matter that much. There are certain situations where missing data makes a big difference, but for most data sets, analyzing it with listwise deletion, just deleting the missing observations, yields basically the same results as these sophisticated algorithms for handling missing data, except for in super extreme cases. And so it was kind of depressing to know that my research would only help edge cases where they have like severe missing data. Anyway, like I said, probably not that big of a deal and probably wouldn't change their results all that much. All right. And then my final critique, it's more like a big picture critique. This sort of thing may or may not be a super big deal. But my critique really comes down to one question. Why? Why are you doing this paper? And so they propose two reasons. One is to see how well neural networks work on stroke data. The problem is this is one data set with some very quirky characteristics that's probably not representative of all stroke outcome sort of analyses. So they are touting their one study as a definitive way to determine whether neural networks are superior to logistic regression. And you can't claim that from one study. Instead, you can say, hey, this worked better for this specific study, and that's great. And you might say, hey, future stroke researchers might look into this, and that's okay. But in order to determine whether a neural network will always outperform or even generally outperform logistic regression, you have to do a Monte Carlo simulation where you vary a bunch of parameters that might matter. You might vary the sample size. You might vary the number of variables. You might vary how correlated the variables are with the outcome. You might vary whether you're looking at a logistic regression versus linear regression. All these different variables are probably going to matter a ton in how well neural networks do relative to logistic regression. And none of these variables are varied in this study. We're only looking at one specific composition of these variables. So you can't really make definitive claims because the characteristics of this study are unique to that study. And more importantly, I think, it's kind of a weird comparison to compare logistic regression models to neural networks, at least in the way that they've done it. So logistic regression was never ever designed for variable selection. And we know very well that it's terrible at variable selection. Neural networks, I don't have that much of a background in neural networks, so I say this with caution. I believe they're way better at variable selection than logistic regression is. And so you're comparing an algorithm with a known massive weakness to one with a known massive strength. And since both the logistic and the neural network used variable selection as part of their process, of course logistic regression is going to do terribly because you're using it for a purpose for which it wasn't designed to be used anyway. So if you really wanted to compare logistic regression to a neural network, the better approach would be to do targeted hypotheses, that you've already done variable selection or you already know what specific hypothesis you want to test, and use a logistic regression model and compare that with the exact same variables to a neural network model. Otherwise, I don't know that this comparison makes a lot of sense. Overall, how do I evaluate this paper? Let's pretend I was a reviewer. Would I reject this? No. But I would definitely recommend a revision. And that revision probably wouldn't be that hard to do. First thing is don't categorize the Barthel index or whatever it's called. Just use the continuous version. There's no reason to categorize it. Very bad idea. 2, I would find some other way to filter variables that doesn't use backward selection and doesn't use these univariate tests. Third thing that I would say is don't handle missing data this way, and also give us a data set that doesn't have the imputed values. And also, more importantly, make sure your data set makes sense. And I would also say, hey, why are my results different? So big picture wise, I would also recommend that they really simmer down now a little bit about your claims. You're not trying to say that this will help all stroke analysis. This is more like, hey, here's something that I did for this specific data set that might work for your data set. Just kind of hedge that claim a bit. And with those changes, I think it could be publishable. In fact, next week, I'm going to implement those changes, the ones that I can implement, and show you how I would analyze the data. And as I do this analysis, I'm going to rely... Oh, that's another thing I should criticize the paper for. They don't have any images. Okay, I was wrong. They have one plot. They have 3 images. The first 2 are conceptual maps sort of things. And then figure 3 shows an ROC curve, which I've never been a fan of ROC curves anyway. But whatever. I would much rather see a scatter plot of the model. Every time you fit a model... Okay, let me say this as emphatically clear as I can possibly say. Every single time you fit a model, you must have a graphic accompanying that model. Otherwise, there's no way for the user to evaluate the appropriateness of the model. So please, there are lots of ways you can plot logistic regression. Use those ways. By the way, you can use FlexPlot if you want. But please, use plots. And next week, I'm going to show you how visualization, totally helps in analyzing these data. Did somebody just say visualization? Yes, I did. By golly, visualization, the most powerful tool in a statistical analyst's toolbox. Yeah?
Well, I like the idea of visualizing stuff, but how do I do it?
Oh man, are you lucky or what? Yeah, because you know what? I just barely finished developing a visualization and data mining course, which this fits nicely into. And did you know that in the month of May, starting in a week and a half, I'm going to be teaching a live version of that visualization and data mining class, which is going to happen on Mondays from 12 to 2 Eastern Standard Time via Zoom with me, where we're going to hang out and talk about stats and answer questions and get personalized training from the Jedi Master, me. I am a statistical Jedi Master. No, I'm not a master. I'm an effing PhD, baby, which is better than a master. Oh, I'm more qualified than Yoda. Wow. Can you believe that? You could be trained by a dude superior to Yoda. So I'm going to leave a link in the description to that live class as well as the non-live class, because I want to meet you and stuff and we can hang out. So tune in next week where I'm going to do a reanalysis of this data set and compare my conclusions to theirs. Does that sound like fun? I sure hope so. All right, peace out. See you next time. Bye. See ya. Toodles. Well, that was a good episode.
Oh dear. We are learning statistics, aren't we?
A statistical master you are. A Jedi you are not,
Didn't know I could do a Yoda, did ya?